So let's start off with number one. This is chapter 10. And you know what? You take a quick look and see how these are numbered. I think this is one of those cases where they're really wonky numbering system. That's easy. And then moderate restart. Okay. So chapter 10, easy 1. I apologize, it's grandfathered in. So which of the following should have the lowest boiling point? What do we need to know to determine the boiling point of something? Actually, not just determine the boiling point, but we're making comparisons, right? What are the factors that influence boiling point? Here we're talking about intermolecular forces. Which one has the strongest intermolecular force would be the highest boiling point. The weakest intermolecular force would be the lowest boiling point. So we're looking for what are the forces that are available? We have ionics, right? We have dipoles, and we have London dispersion to choose from. Very strong, intermediate, and very weak. And you can also have interactions here between ionic and dipole, but these are pure substances, so we don't have to deal with that. So how about sodium sulfate? What kind of compound is that? It's ionic, right? Sodium's a metal, sulfur's a non-metal. That's ionic. So it's going to be very high boiling point. HF. Here we have hydrogen bonding, which is a form of dipole. It's going to be fairly high boiling point. Ammonia. This is an intermediate dipole. Remember ammonia's structure from last semester? Well, I assume you've had this before. The structure of ammonia is like that. Right, so you have a dipole going this way. That would give it a higher boiling point, not as high as this one, but the next step down. Water, we can go to water and just say water's like is hydrogen bonding. Right. How about nitrogen? What type of force does it have available to it? Not ionic. Doesn't have a dipole because that bond is not polar. So it has to be a non-polar molecule. This is the only option it has. That's the lowest boiling point, is nitrogen. All right, let's see. Page down 3. When a water molecule forms a hydrogen bond with another water molecule, which atoms are involved in the interaction? Sometimes it helps to draw a picture. So if you have a water molecule here, right? The bonds are going to be polar in this direction. And overall, of course, it's polar that way. But when we're talking about individual atoms, we want to look at what does this effect have on it? Well, that's a slight negative charge up here. These are slight positives. Okay, so how are they going to orient themselves? They're going to be like this. And so hydrogen on one molecule interacts with the oxygen on another molecule in electrostatic form. So which one of these statements satisfies that? I think B does. Of course, that's obvious, but I've been known to put the wrong answer up there, so it's a good idea to check. I don't know if you guys caught any of them last semester or not. Make some boo-boos last semester. Yeah. Take a few, yeah. Okay. Let me see if I can scroll this a bit. Let's go up some. All right, we're going to have to go back up and look at these others because 4 talks about figures Roman numeral 1, 2, and 3. Which of the following statements are incorrect concerning drawing 3? Oh, okay, so we're good. We only have to look at 3. What are we looking at here with 3? Well, the way it's represented, we've got a chlorine and a hydrogen. That's a covalent bond. The way it's represented, right? And this one's going to be slightly positive, and this one's going to be negative. Okay. So, which of the following statements are incorrect concerning 3? That means we got to look at all of them. Electrostatic interactions exist between the molecules. A. Correct. Electrostatic interactions. This positive with the negative of a different molecule. Okay. The molecules find the best compromise between attraction and repulsion. That's also true. We didn't make a big deal out of that, but that's how they find the lowest energy. Right? Attraction decreases energy, repulsion increases energy, and we want to find a happy medium. Lowest possible energy is the most stable. So they find a compromise. These molecules exhibit ionic bonding. Is that true? Oh, there are no ions there. I mean, we've specified that these are partial charges, not complete charges. So that was false. And OCS exhibits this type of interaction. So OCS is oxygen, carbon, sulfur. In order to make any sense of that one, we'd have to do the we have to determine its structure. Okay. So why don't we do that? It's kind of a review from last semester. So oxygen has how many valence electrons? 6. Carbon has 4. Sulfur is 6 also. So we have 16 electrons, right? And this tells us the order of the atoms. So they're going to be like this. Okay. So we know we have 16 valence electrons that have to be distributed. We're drawing the Lewis dot structure. Okay. So we start from the outside and work our way in. We've got 2 here and 2 here. So that's -4 is 12. Left over. 2, 4, 6, 8, 10, 12. Okay, so we've used up all of our electrons. Now we've got to make an octet for the central atom without losing the octets for the outer atoms. So the simplest way is to move 2 over and make a double bond. Now we could make a triple bond here, and that would work. The problem is if we calculate the formal charge, did y'all do that in the first semester? Formal charge, probably. We'll find that the formal charge would be closer to 0 for everybody if we make a double bond on the other side too, and not put a triple over here. So here's what we've got to go with. There. There we go. Okay. So what we have here is 2 groups around the central atom, which is linear. So this is the way it would appear. A linear molecule. Now, which way would the bond dipoles be? Well, oxygen against carbon is this way, and sulfur against carbon is this way, but they're not equal, right? Because oxygen is up and to the right of carbon, and sulfur is just to the right. It's lower than. So the overall dipole should be roughly that way. Okay. So OCS exhibits this type of interaction. That type of interaction. Yeah, it does. It's a lot weaker than this one because of the difference, the difference in dipoles. I mean, the dipole for this bond is much greater than the net dipole for that molecule, but it still exhibits the same interaction. Now, if we had oxygen on that side, carbon dioxide, it would be nonpolar. It would not exhibit that behavior. But since we have this slight difference between this electronegativity and that one, we do get a net dipole toward the oxygen. Okay, clear as mud. All right. Well, I forgot to write that. That was number 4. All right. So let me see if I can do this. We'll scroll down a little bit. Can I get them all in there? Barely. Okay, 6. Which best explains the following trend? So what is the trend? All of those are noble gases, right? And they're in order in their group from top to bottom. Helium, argon, krypton, xenon. As we go down, notice the boiling point gets higher. Right? So how do we account for that? We can't account for it with ionics, of course. We can't account for it with dipoles because they're just single atoms, right? The only thing we have left to account for a change in boiling point is London dispersion forces. And the bigger the atom, the more probability you have of redistributing electron density around that atom from one side to the other. The electrons have more space to move around. So bigger atoms and bigger molecules, for that matter, that are nonpolar will have higher boiling points because you get that instantaneous movement of electrons around a larger space. That gives you bigger, more frequent instantaneous dipoles, you might say. So that's the explanation, and there's the answer. Only London dispersion forces will account for that difference. I think I mentioned that in the lecture too, shortly. We didn't spend a whole lot of time on it. How about 7? Which of the following compounds has the lowest viscosity? Okay, we're looking for low viscosity. So what do we need for low viscosity? The attractive forces have to be low also. So which one was had to have the lowest attractive forces? Well, we look at our choices, right? Carbon tetrachloride is nonpolar. Water, of course, would be out because it's a hydrogen bond. HCl would be out because it's dipole. This is a huge hydrocarbon. Probably, you know, I think that's even bigger molecule than diesel fuel. It's probably more like axle grease. Because these 25 groups of methyls in the middle. But as these get bigger, I think I did show you that one. As the hydrocarbons get bigger, bigger and bigger, their boiling points and melting points increase. Because that same thing, bigger molecule, you can have redistribution of electron density much more easily and widely. So this one's going to have a higher boiling point, viscosity, viscosity, because of the attractive forces. This one is non-polar overall, but each one of those bonds is polar, carbon to chlorine. So you get on a localized level, you do get some interaction here. But this one is definitely London dispersion only. The least viscous is nitrogen. Nobody thinks of a gas as being viscous, but it can be measured. The other thing you can do is look at the state. You're given the state here, gas and gas. So you can throw the liquids all out because gases are less viscous than liquids by definition. That's another way to look at it. So the answer is B. Nitrogen is the least viscous of all those given. 8, when a nonpolar liquid displays a convex meniscus. What do we mean by that? We got 2. We got a liquid in here, and either it's a capillary and it moves up, or we've got a vacuum up here, and there's air pressure pushing it up. Either way, it doesn't matter. We're talking about the behavior here. This is a convex meniscus, okay, as opposed to a concave. Which of the following explains the behavior? It has a low surface tension and therefore clings to the glass. Surface tension, remember surface tension? I don't think that explains it. Low surface tension means that it would flow easily. It wouldn't, and you drop it on the tabletop and it just, whereas if you drop some water on the tabletop, you know, it kind of beads up. But there's also a, do they say it's in a glass tube? No, the answers say it's in glass. So what forces are being exhibited here? Whether it's convex or concave, what forces are at work? Cohesive forces and adhesive forces. Adhesive forces are here, right, with the container wall. Cohesive forces are here, inside the liquid. So when the cohesive forces exceed the adhesive forces, you get that convex meniscus. Examples, mercury. The other, concave meniscus, the adhesive forces are stronger than the cohesive forces. So you get a concave meniscus, that's example, water in a tube. So the cohesive forces are stronger than the adhesive forces. That's true, right there. All right, 9. Which substance can be described as cations bonded together by mobile electrons? When did we talk about cations bonded together by mobile electrons? Metals. I remember the discussion of metals where we had the electron C model. And then that didn't satisfy, so we moved to the molecular orbital model. So which one of these is a metal? Well, that's an ionic compound. Krypton? Nope. Noble gas? Nope. Non-metal. There it is right there. Silver. Only metals fit that model. So this would be A. Let me see here if I can scroll a little bit. Yeah, there we go. 10. Which of the following statements about steel is false? All right, so we have to look at each one. It contains carbon atoms in the holes of its iron crystals. Is that true? It's an interstitial alloy. About B, presence of carbon iron bonds in the alloy makes steel harder and stronger than pure iron. Yep, that's one way of looking at it. That bonding also, if you look at, you ever seen a slice of metal that's been polished and then photographed in polarized light? They do this with minerals too. It gives you a better picture of the crystal structure. So you get these, some of them you have little tiny crystals, some of them have huge crystals. But when you get those carbon atoms interspersed in the metal, it locks the crystals in place. They can't move. And then you can't get atoms pushing past one another like you could with pure iron. How about pure iron is relatively soft, ductile because it lacks directional bonding? That's true. And that's characteristic of metals. Most pure metals, you can scratch with your fingernail. There are a few exceptions, but most of them have non-directional bonding. The amount of carbon directly affects the properties of steel. Go in. Low carbon versus high carbon. Right? The katana, you know what the katana is? Samurai sword. They make it by forging together soft, low carbon steel in the center of the blade and high carbon steel on the outside. The low carbon gives it durability, flexibility, so it won't break. But the outer side is high carbon steel that can be sharpened to a very razor sharp edge. All of these are true. That's it. They're all true. Nowadays, we're able to combine metals and non-metals and alloys that duplicate the sharpness and durability of the samurai sword in a single metal. We don't have to do the forging together of different kinds, but it works. And it had worked for them for centuries. 11. Which of the following statements is true about P-type silicon? P-type silicon. You know, you write that a little bit bigger. There we go. It is produced by doping silicon with phosphorus or arsenic. How do you need a P-type semiconductor? Right. We'll stick with silicon. You look at the periodic table, and you look to the left would be fewer electrons than phosphorus, which would mean you create those positive holes. So we're looking to the left of silicon. To the right would be N-type, because they have more valence electrons than silicon. So the left of silicon would be what? Gallium, aluminum, indium. A is not true. Phosphorus and arsenic are to the right. Right. So A is false. How about B? Protons are the mobile charge carriers. Can protons move? No, they're stuck with the atom. Right? The nucleus stays put. The only thing that can move is electrons. All right, so this was false. How about C? It does not conduct electricity as well as pure silicon. Yeah, it does. because you've created that difference in charge. And now you can move. The common way to think of it is the poles, the positive poles are moving, but actually the electrons are moving in the opposite direction. You've got mobile charge. Anytime you have mobile charge, you can conduct electricity. Okay. It's like a solid crystal of sodium chloride is an insulator. Okay. It's an ionic solid. You have sodium ions and chloride ions, but they can't move. They're locked in the crystal. The only way to get them to move, well, there are two ways actually. You can melt it and free them up, or you can put it in water and bust them apart, and then they'll conduct electricity. But it does conduct electricity as well as pure silicon. In fact, better. So all are not true. None is true. Easy answer. None of those are true statements. All right, let's see. 14. A solid crystal of sodium chloride. I just gave you the answer to that one. Solid crystal of sodium chloride is soft, low melting, good electrical conductor. Nope. It's hard, high melting, but not a good electrical conductor. So that one's false and that one's false. Soft? Nope, it's not soft. We're trying to economize on time since this you might see a question like this on the exam. I'm going to go through it quick. So how about hard, high melting, poor electrical conductor? Bingo. That's the one. By the way, water is not a good conductor either. Pure water is an insulator. And the only way to make, well, actually there are two ways. Two ways to make water conductive is to put something in it that conducts electricity, like salt or small amount of acid. Or run an extremely high voltage charge through it. What that does is ionizes the water. Now you've got mobile charges. That's what happens in an electrical storm. You know, if you're standing in a pool of water and grabbing onto a flagpole when the light strikes, it'll go down there and right through your feet because the high voltage ionizes the water and takes you to ground. So don't grab the pole and wear insulating boots. Did I tell you the story of a classmate of mine in high school? Yeah. Well, I was a teacher's kid, so this was a private school, and I got a break on tuition. So I thought it was great. You know, I could get, because I knew some people, friends who were in the public school system, and they were getting crappy educations. So I took advantage of it. Anyway, these were rich kids, and they had houses scattered all over the place. They had cabins in the woods and all this. So one of our classmates was alone in a cabin one weekend in Georgia, and she decided to take a bath, bubble bath, with talking on the phone. Storm came through, lightning struck, the phone wire went right down through the phone, through her and into the ground. She was dead. Of course, we had another student, I might as well continue. Another pair of students that decided they were going to climb a power pole. I mean, a really high power pole, like 100,000 volts. And slipped, reached out and grabbed the wire. And got a pretty bad shock, but dropped to the ground, and the shock had just limbered them so much when they hit the ground, they just kind of bounced. So they were injured, right? Burned hands and everything, but didn't kill them. Okay. So what is it that kills you when you get electrocuted? It's not the voltage, it's the current. You get a high current going through your body, that'll stop your heart. High voltage just makes the current flow. But it's It's the current, it's the passage of charge through your heart that stops it. Ask those guys on the Green Mile. They'll tell you. Which of the following has the highest melting temperature? Okay. What we're looking for here is just the opposite of that first one we encountered. So if you've got any ionic compounds here, those are the best candidates, right? Water's fairly high. Carbon dioxide is low. Sulfur is nonpolar. Phosphorus is nonpolar. There you go, magnesium fluoride. That has the highest melting point of any one of those because it's an ionic compound. Which of these statements is false? A diamond is a covalent crystal. Is that true? Yes, it is. Every carbon atom in that crystal is covalently bound to the other one. The size of the unit cell of lithium and cesium is the same. So we're talking about pure substances, lithium metal in its crystal structure or cesium in its crystal structure. Right? Would they be the same size unit cell? Lithium versus cesium. The key there is how big are the atoms. Okay? So remember your periodic trends. Lithium is high in that group. Cesium's at the bottom of that group. So it's going to be the bigger one. This would be the bigger crystal. Now, they may very well be the same type of crystal, right? Simple cube, face-centered cubic, or body-centered cubic. I don't know which one. But this one's going to be the biggest. Right? So they would not be the same. Oh, we found our false one. This says none of the statements is false. We found a false one. We can stop. Right? And the rest are true. In the interest of time, we're going to move on. 17. Let's see, I need to go around here and scroll a little bit. That's good. How would you expect the melting point of carbon tetrachloride to compare to sodium chloride? Carbon tetrachloride versus sodium chloride. Well, the melting point of this one ought to be much, much higher because that's a nonpolar compound and this is the ionic. But we need to read the statements to see because there may be a qualifying reason in there that could be false. So it should be lower. Yeah, that's lower. Because sodium chloride forms an extended ionic crystal lattice, whereas carbon tetrachloride is covalently bonded to small molecule. That's a good answer. Yeah. A is true. Let's see, we got any oddballs down here? No, we found the right answer. They're not both ionic solids. There's no charge in this one, right? Now that's not a charge, that's a formal charge. So this would be a formal charge of +4. It's not a charge. This is a covalent compound. Electrons are shared. So I'm ready to stop there. And move on. Where we draw that one? 19. At normal atmospheric pressure and temperature of 0 degrees. So normal atmospheric pressure is 1 atmosphere. And we're going to say temperature is 0 degrees. See, which phase of water can exist? It's 1 atmosphere pressure and 0 degrees. What can happen? What can exist at that temperature? Ice, right? And liquid water. If we were above or below, then you'd have one or the other. But right on that temperature, you got both of them, ice and water. So that's why A is the answer. Kind of a tricky question. 20. Okay, let's see here. Oops, there we go. There's 20. Which of the following processes must exist in equilibrium with the evaporation process when a measurement of vapor pressure is made? Remember the balance that we're trying to establish when we're doing vapor pressure? At the surface of the liquid, you've got two things going on. You got evaporation and condensation. And they have to be balanced in order for the vapor pressure to stabilize. When you first put it in there, the vapor pressure is going to start climbing because it's only one way evaporation. But eventually you get enough pressure to where they're balanced. So condensation is balancing evaporation. Let's see here. Well, there we go. So let's go back down just to see. There we go. 21. You're given the following boiling point data. Which one of the liquids would you expect to have the highest vapor pressure at room temperature? This is that relationship that we went through on one of the latter slides in this chapter. Right. So as intermolecular forces increase, everything else increases except for vapor pressure. It's the other way around. Because the intermolecular forces are holding things in the liquid phase. So as they increase, there's not as many of them leaving the surface. That's why it's inverted. So what we're looking for is the highest vapor pressure would have the lowest boiling point, which would be that one right there, diethyl ether. Which of the following decreases as the strength of the attractive intermolecular forces increases? Well, that's 21 saying it the same way. Right? The only one that decreases is vapor pressure. So here it is right there. 23. In which of the following processes will energy be evolved as heat? Okay. So if we look at the, let's see, let's put gas up here. Let's put liquid down here and solid over here. So we can go from liquid to solid. Right? That's known as freezing or fusion. Freezing's okay. Okay. Or we can go from solid to gas. And that would be sublimation, correct? Or we can go from gas to liquid. And we've talked about that one already. That's condensation. Okay. Now we go back the other direction. Solid to liquid is melting. Okay. And gas to solid is deposition. And then we can go back this one. Liquid to gas, which is evaporation. Okay, now to answer the question, energy is evolved, that is exothermic, gives up energy. So in that case, you're going from a disordered state to a more ordered state. So gas to liquid, gas to solid, liquid to solid would be an exothermic process. So exothermic would be this inner circuit: condensation, freezing, sublimation. No, that's not right. Deposition. So this one, condensation, freezing, or deposition would be from disordered to more ordered. Disordered to more ordered. Disordered to more ordered. So any one of those would work. Sublimation? Nope. Crystallization. All right, crystallization is another word for freezing. Actually, it's not synonymous, because you can freeze a liquid into a solid and make an amorphous solid. Where crystallization was kind of like a second cousin. So yeah, crystallization would work. Vaporization, nope. Melting, nope. So it has to be crystallization. It's a form of freezing. That was 23. I'm wasting time, weren't I? Let's see, we got a lab. Okay, I'm safe. 25. Choose the correct statement about the diagram below. What I meant was we have lab time available. We don't have a lab. So let me see. Let's go down here and scroll up a little bit. Oh, that's too much. Oops. All right, I'm gonna have to do this anyway. Position it just right. There we go. 26. Below is a phase diagram for compound Q. Okay. It doesn't tell you where liquid, solid, and gas are. You have to remember that. By convention, this is the gas, this is the liquid, and this is the solid. Okay. You want to purify a sample of Q that was collected at 1 atmosphere pressure and 100 K. So it was collected at this position right here. And you want to purify it by sublimation, right? So sublimation means that you want to turn the solid into a gas that will separate it from impurities. So you want to go from the solid to the gas. So how would you do that? Well, our choices are, at this point, this is where we collected it, increase the pressure to 1.5, and then increase the temperature to 300. Now, that'll take it through the liquid phase. Can't be A. Increase the temperature to 300 K. Okay, we're still here. Increase the temperature to 300 K. Now it's gas. You can't sublime it anymore. You've turned it into gas already, right? Actually, you've turned everything that came with it into gas. All right, lower pressure to 0.5, okay. And then increase temperature to 200. All right, now we're going from solid to gas. There you go. That transition goes from solid to gas. It's subliming under those conditions. So C's the answer. That makes sense? Okay. All right. Let's see. What about this one? 29. Given this phase diagram, and the areas are similar, solid, liquid, gas are in the same position, relative positions. The solid has a higher density than the liquid. Okay, this one's kind of a tricky question. Most phase diagrams for pure substances will give you a solid liquid phase line that's positive slope, goes this way. The only one that I know of that goes the wrong way is water. So based on that, if this is water, then the solid which one is false? The solid has a higher density than liquid. No. Water, the liquid, has a higher density than the solid. That's not a good question, I don't think. You? No, I don't think it's a good question. It's the kind of question you see on a standardized exam. ACS exams. They can come up with some really squirrely ones. Okay, now we're moderate. We've been easy up to this point, believe it or not. Now moderate difficulties. 1. Which of the following is the correct order of boiling points for KNO3, CH3OH, CH2, C2H6, and neon? Well, this is one Morgan's familiar. You know, my approach to something like this, when you want to put them in order, is nail down the ends. Okay. Which one has the highest boiling point? Which one has the lowest boiling point? And then you've got 4 of them, so they'll just have to decide which way do the other 2 go. Which one has the lowest boiling point? Has to be neon. It's a noble gas. It's a small nonpolar atom. So neon ought to be the least. How about the greatest? Well, let's look at the possibilities. You've got hydrogen bonding here. Oh, you got an ionic compound there. That's our best candidate for the highest, the ionic compound. Right. So now we just need to say, all right, we've got methanol left over and ethane. So methanol has hydrogen bonding available. So it ought to be here. And that leaves ethane here. Okay. That's D. Okay. Let's see if I can do this. There we go. 4. Assume 12,500 joules of energy is added to 2 moles or 36 grams of water as an ice sample at 0 degrees. The molar heat of fusion is 6 kilojoules per mole. That is, how much heat does it take to melt the mole of water? That many joules. The specific heat of liquid water is 4.18 joules per gram degree centigrade. And the molar heat of vaporization is 40.6 kilojoules per mole. All right, We didn't spend a lot of time during the introductory material on heats of fusion and heats of vaporization. But I did draw the heating diagram. So maybe I better put that in here as an aid. So as we heat things up, then the temperature is going to rise. It's going to go like this, and that, and that, and that. Let's see. Solid, solid, liquid, liquid. Yes, liquid. There. Okay. So in this section, we've got nothing but solid. In this case, ice. In this, we've got transition from solid to liquid. In this one, we've got liquid only heating up. In this one, we've got liquid to gas. And in this one, we've got gas only. Okay, so whenever you've got two phases present at the same time, temperature is stable, stays there. And under these conditions, this temperature is 0 degrees C, and this temperature is 100 degrees C. Freezing point, boiling point. Okay. So the answers tell you what we're looking for. We want to know what's left over when you put that much heat into water that starts here, right at that point. Okay, so we don't have to deal with this right here. All right, so the different processes that are going on are that we're converting solid to liquid. In that case, we're going to put energy into it to convert solid to liquid in this phase right here. So how much heat does that require? Well, we're going from 2 moles of water and 6.02 kilojoules per mole, right? 2 moles of water, 6.02 kilojoules per mole. So this will tell you how much energy is required to melt that ice. All right. So what's that? 12.04 kilojoules. Well, we're in joules, so let's convert that. 12,040. 12,040 joules to melt the ice. And so what do we got left over? 12,040 and 0.6. 60 joules, right? That's all we got left over. Oops, sorry, 460 joules. 460 joules. All right, so now we're at this point right here. From that amount of energy, now we're heating the liquid up. So now we need to know change in temperature equals the specific heat of water times the we just said mass, but we're going to say moles. Let's say N. Actually, the amount of heat, I'm sorry, that's my mistake. The amount of heat is going to be the specific heat. Let's see, S, I think they used. S for liquid water times how much of it there is, and we're using the molar specific heat, not the one with mass, but the one with moles, and then change in temperature. Correct? Okay. So we know what we have available is 460 joules. We know that 4.18 joules per gram degree C is S. This is back to our calorimetry in first semester. How many moles we have? 2 moles. And change in temperature is going to be our unknown. Right? So we solve it for how's the temperature going to change? Well, if the temperature changes to 100, then we know that we're starting to get gas. But if the temperature ends up in here somewhere, we've still got liquid and nothing else. Correct? So let's say delta T equals this one divided by that one divided by that one. Okay. 460. And then we're going to divide it by 4.18 and then divide it by 2. So I got 55. 55.0 is delta T. 55.0 degrees C. So if we started at 0, because that's where we ended up here, we've only gone up 55 degrees. So we're right in here somewhere, right? It's liquid only, right? There's no ice left. There's no gas produced. It's not boiling, in other words. Okay, so only water. It'd been better to say liquid, but it is what it is. All right. Let's see. We got, yep, we're in difficult already. Didn't spend much time in moderate. Difficult 1. A crystal was analyzed with X-rays having 2.33 angstrom wavelength. So wavelength equals 2.33 angstroms. We didn't mention angstroms as a measure of wavelength. An angstrom is equal to 10 to the minus 10 meters. Angle first order diffraction, n equals 1. See where this one's going? Bragg equation. And the angle is equal to 19.2 degrees. Okay. What would be the angle for the second order? Right. Now we want to know, now we want to know this one. At what angle would that occur? This is first order, this is second order. Okay. Now let me see. I think we have oh, okay. Just checking myself. If the wavelength is in angstroms, then the separation, the distance between the layers in the crystal lattice will be in angstroms. So it just depends. If we use meters here, the distance would be in meters. So what's the Bragg equation? Remember? D equals what? N, right? Is it 2 angstroms? That information is useful at the end of your document. You don't have to memorize it. You just have to know, recognize it. Where's that? One out. There it is. 2D side. Theta. There we go. There are 2 approaches to this problem. You can find out what is the separation, and that's going to be fixed for this crystal, not going to change. Then you can set up the equation a second time, and this time change that and put the value you determined for the first determination here. And that gives you the same wavelength we use here. This is 2 now. We put in the value determined for the first and then solve for the theta. That would be the angle here. That's probably the best way to do it, simply because it follows a pattern. We could do it algebraically. We could say this one is 1 for that one. We could set up 2 equations, and then we could we're going to solve this one for D, and then we could substitute what it's equal to. D is equal to something, substitute it in the second equation, and then just do it the whole calculation at once. Right? But that'd probably be too confusing. So let's do it step at a time. So this is going to be 1, right? This is going to be 2.33 angstroms. This is going to be 2. That's our unknown, and then sine 19.2 degrees. Okay. So to solve that, this one is divided by 2 and divided by sine 19.2. So 19.2, let me take the sine. It's in here somewhere. There it is. And I'm going to say 2.33, divide that into it, and then divide 2 into that. So I get 3.54 is the distance. 3.54 angstroms is the distance separating the crystal lattice. So now we can set up another equation. This one now will be n will be 2. The wavelength is still 2.33 angstroms. And this is 2. And the distance now is 3.54 angstroms. And then this sine theta. Now we solve for sine theta. So this one divided by that one, right? These 2's cancel out. So I just need to say 2.33 divided by 3.54 is equal to sine theta. So what am I looking for to find theta? The arc sine of that value. It's analogous to the inverse. The arc sine of sine. So where are you going to find that on your calculator? It's usually a function above where the sine key is. Mine says a sine. So I take that value and I take the arc sine of that, and that's 4.12. So this is 4.12 degrees. So that will be the angle at which you will see the next peak as you're scanning that crystal. You scan it down at 19.2 degrees, get your first peak. That's the fundamental. And then the first, music overtone. The next one will be at 4.12 degrees. Excuse me. No, 41.2. Sorry. 41.2 degrees. So it'll go down here and then you'll go down there like that. And you'll get another strong signal because of the nature of interference. Or you just learn how to use the equation. So that was B. B's the best answer. I rounded up to 2. So like I always say, if you have no other choice, pick the best answer. So 2, chromium metal crystallizes as a body-centered cubic lattice. Okay, so we've got chromium, solid, and we know that the unit cell is a body-centered cube. Remember what the body-centered cube looks like. So we've got a chromium at each one of these corners. And we have a chromium right in the middle. That's a body-centered cube. If the atomic radius of chromium is 1.25 angstroms, so radius equals 1.25 angstroms, what's the density of chromium metal in grams per cubic centimeter? So we're looking for density. All right, what do we need to know to answer that question? We need to know mass per unit area. So let's do the area first. If we know the radius of the chromium atom, and we know this unit cell, what is the length of this side? Because if we find the length of this side here, we can find the length of that side. All we have to do is cube it. We got the volume. Oh. Yeah. It's not area, it's volume. Okay. So if you look in useful information, BCC, body center cube, the formula is 4R over square root of 3. They're using A, so let me be consistent here. A. So that distance A equals 4R divided by the square root of 3. Okay. So if we plug in the numbers, 4 times 1.25 angstroms, we'll change units in a minute. Divided by the square root of 3 equals what? This will give us the side of the cube in angstroms, and then we have to convert it to centimeters. So 4 enter 1.25 times 3 square root, divide that into it. So I get 2.887 angstroms is equal to the side on that cube. Okay. So how many cubic centimeters is that? Well, we have to know what the conversion is. Okay. I just told you that angstroms is 10 to the minus 10th meters. Right, 1 angstrom is that. That's not cubic centimeters. I mean, that's not centimeters. Right. So we're going to have to chain it together. This is dimensional analysis. So get rid of the meters and leave centimeters. There are 100 centimeters in a meter. Okay. So that will give us centimeters. Right. All right. 2.887. And then this is 10 to the minus 8, right? Oh, we can do that. 2.887 times 10 to the minus 8 centimeters. So the volume is equal to this cubed. And let's see, where here it is. That's not right. We do that again. 2.887 exponent there. Cubed. So I get 2.41 times 10 to the minus 23rd cubic centimeters. So now we've got the volume. How do we get the mass? In this unit cell, how many atoms are there? Remember when we determined that in class? For the body-centered cube, that atom belongs to that cube. So there's 1. But for each one of these, only 1/8 of each one belongs to the cube. So we got 8 of them. That means there's another one. So we have 2 atoms. 2 atoms of chromium per cell. Right? We want to convert that to grams. So how many atoms are in a mole? Right? Because the only way we can get there is to use molar mass of chromium. That's the only relationship we've got that will get us to mass. 6.022 times 10 to the 23rd atoms per mole. Right? That gets rid of atoms. Now we need to convert moles. to grams. So what's the molar mass of chromium? Now let's see, 51, well, round it off, 52.00. All right, so now we're going to find the mass of chromium in that unit cell. Okay, I get 1.727 times 10 to the minus 22 grams. So the density is going to be that many grams divided by 2.41 times 10 to the minus 3 cubic centimeters. Let's see, I just need to get them in my calculator, flip those and divide. I get 7.18 grams per cubic centimeter. B is the answer. Okay. That took a few steps. That's why it's in the difficult section. All right. A magic wand. Oh, chapter 11. So that's it for chapter 10. Now we're going to chapter 11, starting with easy. In a 0.1 molar solution of sodium chloride in water, 0.1 molar sodium chloride aqueous. Okay, that's our starting point. Which one of the following will be closest to 0.1? Mole fraction, mass percent, molality. If you're in a hurry, the safest bet is molality. Because with a dilute solution like that, remember the definition? This is moles per volume in liters of solution. And molality is moles per kilogram of solvent. When the solution is really dilute like that, these are virtually equal, right? Because 1 kilogram of water is 1 liter, right? And if you got just a tiny amount of sodium chloride in there, it doesn't change that value much. So your safest bet is to go with molality. Molarity and molality are very close for dilute solutions. The problem is, if you're running an experiment that's temperature dependent, then you have to use molality because it gets around temperature with mass instead of volume. We could go through and calculate each one of those if we had time. And I think the work problems does that. But in the interest of time, we're going to move to number 2 now. Which of the following concentration measures will change in value as the temperature of solution changes? Okay. Well, mass percent, no, because it's based on mass only. Mole fraction, it's based on number of particles. That doesn't change with temperature. Molality, right? We just argued that one. It doesn't change. Molarity does change with temperature because it's based upon volume. Three. Let me see if I can do this. Down here. There it is. Here we go. Number 3. Which of the following chemical or physical changes is an endothermic process? Put energy in. Evaporation of water? Yeah, and since E is none of these, we found our answer. When water evaporates, you've got to increase the kinetic energy of all the molecules in water to get them into the gas phase. Right? When you recognize the difference between liquids and gases, they're very far apart. The gas molecules are moving really fast. The only way you can get there is to add energy. Oh, we got physical changes too. I mean, chemical changes to deal with, right? Endothermic versus, okay, so A, yes, A is correct. It's an endothermic process. Endo. Combustion of gas, exothermic. Right? That's why we can operate our car. It gives off heat. The engine in your car is otherwise known as a heat engine. It works on the same principle as a steam engine or various types of heat engines. Let's move on. So B is not. C, the mixing of sulfuric acid and water. Remember their rule, safety rule? Is you ought to add acid to water. You do that because with lots of water and a little bit of acid, it's extremely exothermic on a molar basis. So when you add just a little bit of acid to water, the volume of water can absorb that heat. If you add water to sulfuric acid, concentrated sulfuric acid, the water will instantly vaporize and splatter acid up in your face. So that's why you add acid to water instead, because it's exothermic, extremely exothermic. That works for bases too. If you have a concentrated solution of sodium hydroxide and you want to dilute it, you add sodium hydroxide to water. Freezing of water. When you go from less ordered to more ordered, you have to give up energy in order to get those molecules closer together and lower their energy state. They have to give up energy. That's exothermic. All right, so A is the answer. Or, which statement about hydrogen bonding is true? Okay, we're talking about hydrogen bonding. Hydrogen bonding is the intermolecular attraction forces between two hydrogen atoms. I don't think so. All right, so what do you have with hydrogen bonding? You have an electronegative atom and hydrogen, and then it can be connected to something else. But this one is either fluorine, oxygen, or nitrogen. And that gives you a slight positive charge here. Excuse me. I'm thinking. Slight negative here and a slight, you can write with Greek letters. There we go. So the attraction between two molecules is between this one on this molecule and that one on the other molecule. Right, so A can't be it. The hydrogen bonding capabilities of water molecules cause that molecule to be more soluble in water than this one. No. There's no hydrogen bonding there. Right? It doesn't have an oxygen or a fluorine or a nitrogen. Hydrogen bonding of solvent molecules with a solute will not affect the solubility. I beg to differ. Hydrogen bonding is very influential on the solubility. I mean, just ask sucrose in water. You can put more sucrose in water than there is water because of hydrogen bonding. How about hydrogen bonding interactions between molecules are stronger than the covalent bonds within the molecules? Well, we know that can't be true. Otherwise, the intramolecular bonds would be ripped apart by the intermolecular bonds. So we're only left with E. Hydrogen bonding arises from dipole moment created by the unequal sharing of electrons within certain covalent bonds within a molecule. That's as close as we're going to get in this series of statements. So E is it. Five. Which of the following favors the solubility of an ionic solid in a liquid solvent? Okay, it looks like we're looking at stepwise process for solubility. So if we have an ionic solid, let's take, for example, sodium chloride. We want to put it in solution, aqueous solution, let's be specific. Okay, what has to happen? Well, first of all, you've got to separate these ions. Right? There's a positive, there's a negative. So we've got to have separate ions. Okay. Then you have to hydrate them. You've got to add water molecules to each one and form those ion and hydrogen bond interactions, electrostatic interactions. Let's see. Solvation energy. Okay, solvation energy is this, going from here to here. When you solvate these ions, this requires energy. You got to break that bond apart, and then you got to form these. So the net there is solvation. No, that's not right. That's not right. Solvation is this one, where you form the bonds with the solvent. That's solvation energy. Lattice energy of the solute. The lattice energy is, did we do this last semester? I think we did lattice energy, where you have gaseous sodium and gaseous chloride yields solid sodium chloride. And that energy is very exothermic. It's negative. Okay. So a small magnitude of lattice energy of solute, which of the following favors the solubility? Large polarity of the solvent. Well, actually, the solvation energy, drawing them together, a large lattice, a small lattice energy, easy to get them apart. So this attributes that change right there, right? Getting them apart. Small amount of energy required to get them apart, then you get a lot of energy back by solvation, right? So that covers these two, and they're both true. A large polarity of the solvent. Well, yeah, that fits in here. Right? Large polarity here means that these bonds are going to be very strong. So all of the above are true. All three of those are true. All right, I see. I'm going to have to scroll a little bit down here. That's good enough. 6. Solid KF has a lattice energy of -804 kilojoules. KF. I think this is the one where we got KF versus RBF. Rubidium fluoride. So the lattice energy of KF, lattice energy KF over here is -804 kilojoules per mole. And the lattice energy for rubidium fluoride is -768 kilojoules per mole. Heat of solution. This one is -15. And the heat of solution for this one is -24. There we go. That's everything that we're given. Which salt forms stronger attraction with water? So the question is, which one stronger attraction with water? This is solvation energy. Let's do this. Okay. I'm gonna go to my crew notes. Yeah, stay on track and focused. All right, so the lattice energy for this one, the lattice energy is like I did before. This one gas plus this one gas yields. Okay, we have solid. And for this one, it's rubidium gas plus fluoride gas yields rubidium fluoride solid. There we go. That's what the lattice energy means. This heat of solution. What does heat of solution mean? Well, okay. Remember when we said the heat of solution is actually broken into 3 parts. The first part, let's do it this way first, because this is the way it shows up in the slides and in your textbook. So the first one, we gotta get these things apart, right? Break them apart into individual ions. This is the lattice energy. But the lattice energy is putting them together. So we need a negative in front of that. Okay? Because we want to go the other direction when we're putting them in solution. And this value is for that direction. So we want to go the other direction for that one. So the second one is we need to, it's called solvent expansion or make a hole. So this delta H is make a hole. So we're taking the water and spreading them apart. How much energy does that take? And then the last one is the actual heat of solvation. That is when this ion or that ion combines with water molecules. That's the heat here. That's exothermic, and this is endothermic. Okay. Which one do we know? Well, we know this one goes in here. For each one, it would actually change the sign and be a positive number. So for this side, it would be 804. For this side, it'd be 768. But we don't have a separation here. We do know this one, right? For this compound, it's -15. So that's the total. All right. So this is the total for that one. This is the total for that one. It's a negative. So for a woman, for this side, we'd have that equal to 804. And for this side, we have it equal to 768. And then we have a term in here that is relative to these two right here. So that one would go in there. that one would go in there. Okay, now this one is equal to minus 15. This one is equal to minus 24. All right, I lose you yet? Yeah. What I'm trying to do is say that these three processes are involved for either one. And we know what the net result is here and here. But this one, where you make a hole in water, is going to be the same for both of them. So really the difference in here is due to the heat of solvation. Okay. So let's see what our choices are. KF, which forms stronger attraction with water? That's the heat of solvation. That's this third step where you have attraction between these ions and water molecules. Okay. So if this is going to be the same, then if we say, all right, keep this on one side, put this on the other side. So this is a minus 819 kilojoules. And this one is a negative 792 kilojoules. Okay, so we're comparing these two. And since the delta H for making a hole in water is the same, then these differences can be attributed to a difference in heat of solvation. This is an exothermic process, so the heat of solvation for KF should be much higher. All right, so KF has a stronger attraction with water, but not because of the lattice energy. It's because it has a more negative heat of hydration. That's this one. The heat delta H solvation is the heat of hydration. Okay. And it took a while to get around to that one, but it's actually in the wrong place. That's not an easy problem. Or did I move into a difficult and didn't realize it? I don't think I did. Yeah, it's out of place. That's a difficult one. Let's see. Well, we have class period is 2 hours and a quarter. Most students don't take that long, believe it or not. 7. Use the following drawing of a gaseous solute in equilibrium with a solution to help answer the question below. Which of the following statements are true when the piston is pushed down? Okay. This is Henry's law. Right? You push down, you increase the pressure of the gas over the solute gas over the solution, and more of the gas goes into solution. Okay. So with that in mind, what will happen? This will cause the pressure of the gas to increase and the concentration of the dissolved gas to go down. Nope, just the opposite. Dissolved concentration goes up. This will cause the pressure of the gas to decrease. No, it won't. This will cause the pressure of the gas to increase. Yes, this is C. And the concentration of the dissolved gas to go up. That's it. We found our answer. And if we, let's see, look at E. No, that can't be it either. So it has to be C, excuse me. This will cause the pressure of the gas to increase and the concentration of the dissolved gas to go up. That's Henry's law. And you don't even have to know why. 8. Which of the following correctly states the relationship between temperature and solubility of the substance in water? Okay, temperature versus solubility. That's the relationship we're looking for. The solubility of a substance in water increases as the temperature rises, especially for gases. That's the disqualifier. It's the other way around. Increase the temperature and gas solubility decreases. If you want to see that not in action, just fill a pan full of water from the faucet, stick it on the stove, and start heating it up. Before it has a chance to boil, and you check the temperature while you're going. Before it gets to boiling point of water, you see little gas bubbles coming out. That's dissolved gases in the water being driven out of solution by an increase in temperature. So A is wrong. A is false. How about B? The solubility of a substance in water decreases as the temperature rises, especially for ionic solids. Well, generally speaking, solubility of ionic substances increases with the temperature increase. There are a few exceptions. The solubility of a substance in water with temperature cannot be accurately predicted, especially for ionic solids. That is true. We've not found a way to predict that solubility. Solubility of a substance in water decreases as the temperature lowers, especially for gases. No, as the temperature drops, gases become more soluble. Right? So D is wrong. C is the only one that's right. All right, 10. A solution contains 1 mole of liquid A and 3 moles of liquid B. So we got this solution, and it has 1 mole of A and 3 moles of B, right? Yeah. This solution has a vapor pressure of 314 torr at 25 degrees. So the total vapor pressure right here is equal to 314 torr. Okay. Still at 25 degrees, pure A has a vapor pressure of 265. So PA equals 265 torr. And pure B is 355 torr. Okay. Which of the following is true? Well, what's the contribution of A to the total? It's 1/4, right? Because we've got 4 moles total. 1/4 of them are A. So 1/4 of this is what? 265 is 66.25 or 66. This one is 3/4. Contribution of B is 3/4 of 355. Yeah. Is 266. So if this were an ideal solution, then the vapor pressure would be the summation of these two. 12, 13, 332. So it should be 332 torr if it were ideal. So what kind of deviation do we have? We have a negative deviation. In other words, that curve is like this, right? Where we have one going this way and one going, let's see, one going this way. Yeah. So you add them together, excuse me, should be over here and over here. So this one should be the ideal, perfectly straight, but it dips. So why does it dip? The negative deviation is due to the fact that when these are together, they are more attracted to each other than A is to itself and B is to itself. And that decreases the vapor pressure. So let's answer the question. This solution exhibits a positive deviation? No, it's a negative deviation from Raoult's law. Okay. Hearing no arguments, we'll move on. A cucumber is placed in a concentrated salt solution. What will most likely happen? So we put a cucumber, a slice of cucumber, put the seeds in it. And we put it in a concentrated salt solution. Let's just say sodium chloride concentrated. Okay, what's going to happen? Compare the solute concentration inside the cucumber with this outside the cucumber. Which one's higher? That, right? That makes it hypertonic. And the water is going to flow which direction? That way. It's going to shrivel up. Right, become very limp. So the water will flow from the cucumber to the solution. Okay. That was easy. Let's see, 13. Osmotic pressure depends on all but which of the following? Okay, what's the formula for osmotic pressure? Let's see, we need molarity, we need the gas constant, and we need temperature, correct? That's the formula. And it should be in the back of your useful information. It's verified. Trust but verify, Ronald Reagan. Let's see. Wait a minute, which one is this? That's 10. It will be in that one. It'll be in 11. Well, let me just look at the exam, make sure it's there. I haven't found it yet. Ooh, okay. Isn't there at all? Okay. Either memorize it or ask me on during the test. So, what are the factors that are involved here? Atmospheric pressure. I don't see a pressure term in there. Well, this one, of course, has a pressure term in it, but that's not a variable, that's a constant. Temperature varies. Right? Molarity of the solution varies, B. Temperature varies, C. Ratio of moles to volume, solution volume is another way of saying molarity. Right? So which one? All of the above. Osmotic pressure depends on all but which? Atmospheric pressure. It doesn't depend on atmospheric pressure at all. Let's see. 14. Shaving cream is an example of which kind of colloid? What do you think? It's a foam, right? It's a gas in a liquid. Shaving cream is a foam. What's an emulsion? A liquid in a liquid. What's a solid? Gas in a solid. Coagulate's not a colloid type. That's what happens to a colloid. when it's destroyed. Coagulation. Oh, aerosol. Aerosol is either solid or liquid in a gas. So fog would be an aerosol. Smog would be an aerosol. I drove through some fog this morning. I couldn't find my fog lights. New vehicle and all that. I found out where they are now, so if it happens again, I'll be ready. Let's see. Moderate. We finally got to moderate after doing some difficult ones. There we go. So let's scroll down to 3. I think all 3 is in there. Yeah. 0.2 molar solution of solute X. 0.2 molar X in benzene. Okay. Displays an osmotic pressure given by the formula. I equals 0.1 RT. Which of the following is most likely to be the case? Okay, notice the difference here. That's the actual concentration. So what we're dealing with here is the modified version, I equals MRT. And this is that, both of those together. Okay, so you everybody see that? This is the Van Hoff correction. When does the Van Hoff correction become effective? When there's dissociation. Usually, that's the one we discussed in class. So sodium chloride produces 2 ions when it goes into solution. Van Hoff correction is 2. Calcium chloride produces 3 ions. Correction factor is 3. Sodium phosphate produces 4 ions. I equals 4. This one goes the other direction. So if this value here is 0.1, but the concentration started off at 0.2, then what does that mean? Van Hoff has to be 1/2. 1/2 times 0.2 is 0.1. I see that? Okay, so why would it be 1/2? It's not dissociating. It must be pairing. Right? You must have benzene, you must have X pairing into something like that in solution in order to get 1/2 instead of the other way. So the answer to that one should be X exists in benzene as X2. Okay, kind of tricky. We only talked about the other way. And then you get one of these questions that goes to, right, trying to give your brain whiplash. Okay. 4. Which of the following solutions, 0.1 mol sodium chloride, 0.1 mol sodium chloride, 0.15 mol sucrose, glucose, excuse me. There is a difference. And 0.1 mol calcium chloride would have the highest vapor pressure, the lowest boiling point. Okay. Highest vapor pressure would be the one with the lowest concentration. Because as you increase the concentration, you decrease the vapor pressure. And these are all non-volatiles. So Reynolds law would be the simple form. We don't have to deal with just one concentration. So which one would have the, what would this be equivalent to? This would be equivalent to 0.2 mol ions. This would be equivalent to 0.15 mol glucose because it does not dissociate. And this one would be equivalent to 0.3 mol ions. Okay, so we're looking for the highest vapor pressure. Highest vapor pressure would be this one, right? Has the lowest concentration. And the lowest boiling point. Right? Boiling point elevation with high concentration. So low concentration will give you the lowest boiling point. That's glucose again. Yeah. Glucose for both of them. Okay. I'm gonna leave that there because I got a sneaking suspicion the next one. Yeah, the next one uses that same information. Okay, now we're going to go probably the other direction. The lowest vapor pressure will be the highest concentration, calcium chloride. And the lowest boiling point, would be the one that has the lowest concentration, which would be glucose. Okay. Lowest concentration, highest concentration for the first one, lowest concentration for the second. Are we good? I see a wrinkled brow. I'm looking for visible signs of distress. Okay, now we're difficult. Okay. 2. I need to change the numbering system for this one. If I do that, then I'm going to change all my work problems. So it's not likely to happen anytime soon. A solution is prepared from 53.8 grams. 53.8 grams of a non-volatile, non-dissociating solute in 85.0 grams of water. Okay. The vapor pressure of the solution at 60 degrees is 132. So vapor pressure of the solution at 60 degrees is equal to 132 torr. The vapor pressure of water at 60 degrees is 150 torr. Okay. What's the molar mass of the solute? All right. So I'm going to get my cheat sheet so I can not wander. 2. Here we go. All right. I'm going to need more board than that. So I'm probably going to have to erase some stuff as we go. So what do we need to know the molar mass? That's the question. What's the molar mass? So I abbreviate molecular weight. We need to know mass per moles. Right? So do we have mass? Yep, right here. There's our mass. So we got mass already. Let's put mass in here so I can erase that. 53.8 grams. Now we need to know how many moles does that represent? Okay, so now we're looking at Rayleigh's law. Okay. The pressure of the solution, this is equal to the mole fraction of water times that pressure right there. Okay. All right, so this is the pure water. So that's 150 torr right here. Erase this one. And this is the resulting pressure of the solution. So now we can solve for the mole fraction, and that will tell us the relationship of this one to the total. Right? That'll give us the mole fraction of water. Right? So the mole fraction of water is equal to 132 over 150. Let's calculate that. .88 is the mole fraction of water. So what's the mole fraction of the solute? 1 minus 0.88. Correct? You only got two components in there. If this is water, then the rest of it has to be 0.12. Well, actually, I don't need to know that. I mean, it's true, but to work the problem, we're going to say, what is this equal to? Right? 0.88 mole fraction is what? It's the moles of water divided by the moles of water plus the moles of solute. Okay. So we know how many moles of water there are? Yeah. 85 divided by 18.02. That's grams per mole. So if we divide 85 by 18.02, I get 4.717. 4.717 moles of water. Okay. So that means this is 4.717 over 4.717 plus moles of solute. Okay. Now I've got an equation with one unknown right there. You just solve for that one unknown. I'll tell you what. Let's make room and go the other direction. So this times that, 0.88 times 4.717 plus moles of solute equals 4.717. So far, so good. So this times that and this times that. So this is 4.151 plus 0.88 moles of that equals 4.717. So 0.88 equals this one minus that one. That was my mistake. 566. 0. Now n equals what? 0.88. Here we go. 0.6432. It was a math error. Okay, divide that into 53.8. And I get 83.6 grams per mole. There we go. E. That's why it's difficult. It's easy to make mistakes. All right. The logic was sound. Math was not cooperating. MF4. You have a 10.4 gram mixture of table sugar and table salt. Okay, so we've got mass of mixture equals 10.40 grams. When this mixture is dissolved in 150 grams of water, okay, so the mass of the solvent equals 150 grams. The freezing point is found to be minus 2.24 degrees. So the change in temperature, freezing point of pressure, is minus 2.24 degrees C. What's the percent of the mass of sugar in the original mixture? We did one of these in class, didn't we? I'm pretty sure we did. Okay, we're going to need to know the molar mass of water, of salt, sodium chloride, and I calculated that as 58.44 grams per mole. And for sucrose, molecular weight of sucrose equals 342.3 grams per mole. We'll need that. Okay, calculate the percent by mass of sugar in this original mixture. What's the percent by mass? Sucrose percent by mass. That's the question. Okay. So we know that the basic expression is freezing point depression. Freezing point depression is equal to I times the constant for water times molality. Okay. This is the change in temperature right here. But we've got two things here, and the change in temperature is going to be additive based upon both of them. So this change in temperature is actually going to be the result of I for sodium chloride times K times molality of the sodium chloride, plus I for the sucrose times K times molality of sucrose. Know that. All right, so we can set up an equation with 2.24 is the freezing point depression, and we use the absolute value here. Okay. So for sucrose, I is 2, and K is 1.86. Let's see if that's, be sure it's given. It's given. It's not given in the problem. Yeah. It's degrees C per kilogram. Multiply. Okay. And then molality of sodium chloride. So that's our unknown for that one. And then this one is 1 for sucrose, and this is 1.86, and this is molality of sucrose. Okay. At this point, we've got a problem because we don't know the molality of each one. So what we have to do is devise an expression for molality. Well, we can solve this molality is what? It's moles of sodium chloride per kilogram of water. And this is moles of sucrose per kilogram of water. Okay. So how much water do we have? Mass of the solid, 0.15 kilograms, right? 0.15 kilograms. So this is going to 0.15 kilograms of water, and this is going to be 0.15 kilograms of water. Right, so we know that. All right, so let's see if we can reduce this equation and keep these two unknowns on one side of the equation. How about that? Let's see. We can factor this one out here, 1.86. Let's do that first, 2.24, and then factor out 1.86, and also factor out 0.15, 0.15. So we got rid of this one, that one, that one, and that one, and now we have left over 2 times moles of sodium chloride plus 1 times moles of sucrose. Yep. Okay. So let's put these on this side. So it'd be 2.24 times 0.15 divided by 1.86. Messed up. But again. There we go. 0.1806. 0.1806 equals these two. 2 times moles of sodium chloride plus 1 times moles of sucrose. There we go. So now I'm going to have to erase some of this stuff. I'll leave that there for now. Now what we're going to have to do is go back to the question, percent by mass of sugar. So percent by mass depends on if we let sucrose, the mass of sucrose, equal our X, then the mass of sodium chloride is equal to 1 minus X. Excuse me. No, it's not. It's equal to 10.40 minus X. There we go. And in order to calculate the moles of this one would be divide that by 342.3 equals moles of sucrose, and divide this one by 58.44 equals moles of sodium chloride. Okay. So now we got something we can work with. If we substitute in moles of sodium chloride for this one and moles of sucrose for this one, then we get a new formula. So we have 0.1806 equals 2 times sodium chloride, 10.40 minus X over 58.44. Okay, and then we add to that 1 times X divided by 342.3. Okay, so now we've got an X, which means X is the mass of sucrose. So save time, the mass of sucrose should be 5.60 grams. That means 10.40 minus X should be equal to, well, actually, we don't need that. If we're going to do what? Percent by mass? Percent sucrose then would be 5.60 divided by 10.40 times 100. And that should be equal to 53.8%. So that's why this was difficult. Notice I skipped over the calculation part because I probably make a mistake anyway. So the nearest answer to that one is C. How are we doing on time? 10:20. We go till 10:45, is it? Or is it 10? Oh, yeah, 10:25. 10:30. And then we got lab time that we can use. Okay, 4. There's my magic wand. Oh, that's it. Yeah, that's all there is.